Let us talk about serialization and deserialization of binary tree. Let us first define serialization. In serialization, we are given root of a binary tree. So when we say we are given root of binary tree, we mean that we are given pointer to the root node in C++ and reference to the root node in Java. So we are given root and our task is to convert this binary tree into a string or an array in such a way that we can construct the tree back from this information that we store in a string or array. The process of converting a binary tree into an array or a string is called serialization. And the reverse process, which is converting an array or a string which has all the information about binary tree back into the binary tree, is called deserialization. So serialization is given root of a binary tree, convert it into an array or a string. Deserialization is you have serialized, you have a string or an array and you want to construct the binary tree. So when we say construct the binary tree, we mean we construct the root node, we construct its left child, right child and then their children, and we have a linked representation and we return root of this linked representation. Before we talk about solution of this problem, let us talk about applications of this problem. Consider a situation where you have tree data structure and this tree might represent anything in RAM, any hierarchical information in RAM. Now if you wish to send this tree structure that you have in RAM across the network to some other device. See, if you are working within a same process or program, you can pass root of this tree, pointer to this or reference to this, and the other function can take the pointer and can work on it. But if you wish to send this across the network, then you need to serialize this in the form of a string so that the string can be sent across the network. Another application of serialization and deserialization is if you are setting up binary tree problems, practice problems like practice.geekspace.org, you need to write test cases. And for writing those test cases, you need to generate strings so that the people whose programs you are going to test against a problem or predefined test cases, those programs are going to read these strings and then construct the tree. So generation of the test cases is called serialization. And when a user's program reads those test cases to construct the tree, that is called deserialization. Let us define the problem more precisely. If we are programming in C++, then we need to write two functions, serialize and deserialize. And for simplicity, I am using vector here, not a string. The main idea is to avoid string operations. Similarly, in Java, I am using array list here instead of using a string. So our serialize function is going to take root of binary tree as an argument and it's going to fill the root's content in this array, right? Our deserialize function is going to take this array as an argument and it's going to return the root. So serialize function fills the data into the array, deserialize function takes the array, constructs the tree and returns the root of the constructed tree. In Java, we have array list instead of vector. So our serialize function is going to take root and an array list and it's going to fill the data in the array list. And our deserialize function is going to take the array list and it's going to return root of the constructed binary tree. Now please pause this video and try to write down the serialize and deserialize functions. A naive approach to solve this problem is to store in-order traversal and one of the other traversals, like either store pre or post or level order traversal. So if you have in-order traversal and pre-order traversal, or if you have in-order traversal and post-order traversal, or if you have in-order traversal or level order traversal, you can construct the tree back. This solution requires two traversals of the binary tree. One is in-order traversal and one more traversal out of the other three traversals. Now think of an approach that does binary tree traversal only once, stores only one traversal in an array with extra information that being stored in such a way that we can construct the binary tree back from this array. Let us now talk about the solution. The idea of the solution is to use a special marker for nulls. Here I have used -1 for null. I am assuming that -1 is not present as data in the given binary tree. We use any of the standard traversals. I have used pre-order traversal here. We can use in-order traversal or post-order traversal or level order traversal as well. We do one of these traversals. While traversing, if we see a null, we store -1 in the array. And this is how we do serialization. Now to deserialize the binary tree, we traverse this array using the same traversal. If I've done serialization using pre-order traversal, then I'll deserialize also using pre-order traversal. Now using the same traversal, we traverse the array. Whenever we see a -1, we mark that node as null in the construction as well. And this is how our serialization and deserializations work. Here are examples of serialization using pre-order traversal. So we do pre-order traversal of this tree. We begin from 10, then we come to 20. So we have 10, 20. Then 20's left is null. So we store left of 20 as -1. Then 20's right is also null. So we store -1. Then we come to 30 in pre-order traversal. We put 30 in the serialized array. 30's left and right are -1. So we store -1 here. Now talking about this example, we do pre-order traversal. We print 10, then we come to 20. 20's left and right are null, so we have -1 after it. And then we have 10's right also as null, so we'll have -1 for 10's right as well. Now let us see this tree. We begin with 10, we come to 20, then we come to 30. When we come to 30, we see left of 30 is null, so we put -1. Right of 30 is 40, so we put 40. Now 40's left and right are both null, so we have -1 two times. Now we go back and we try to traverse 20's right. 20's right is null, so we put one more -1. Now we go back and try to traverse 10's right, and 10's right is -1. 10's right is null, so we put -1 here. So this is how we are going to do the serialization. Let us now see deserialization process. We'll again do pre-order traversal. We'll start traversing this array that we have constructed. We'll begin with 10. We'll make it root. Now we'll see the next node as 20, which is going to be the left child of it. Because in pre-order traversal, we recursively call for the left child. When you recursively call for the left child, you will see that 20 is present. So you will mark it as left child of its parent call. Then you will come to -1. So when you come to -1, you have mainly called for 20's left child, right? This is how pre-order traversal works. So you are going to mark this as null. Then you are going to recursively call for 20's right child. And then you will see again -1. So you'll mark it as null. Now 20 is constructed. You will give the control back to the caller. That's how pre-order traversal works. Now 10 gets the control back, and 10 is going to call for right child. When it calls for the right child, it's going to see 30 in the array. Then it's going to construct the node 30 and going to make it as right child. Now when you call for 30, you are again going to call for its left and right children. When you call for its left child, you are going to see -1, so you're going to have it as null. When you call for 30's right child, you are again going to see as -1, you are going to mark it as null. Let's now see this one. We begin with 10. We make it as a root. Then we recursively call for the left child. When we call for the left child, we see 20 is present here. So we make its left child as 20. Now we make recursive calls for 20's left and right children. Both are -1. So we'll mark both of them as null. Now we are going to give the control back to the 10's call. And 10's call is going to call for the right child, and we are going to see -1 here, so we are going to mark this as null also. Let us now see this array. We begin with the first element. We are doing pre-order traversal again. We make it the root. Now we call for its left child. When we make a recursive call for the left child, we see 20, so we are going to make 20 as left child. Now we are going to first construct this whole subtree, then we are going to make a call for the right child. So when you construct this subtree, you will make recursive calls for 20's left and right child first, and then you will first construct 20's left child. So when you make a call for 20's left child, you will see 30. So you will make 30 is left of it. Once you come to 30, you will make a recursive call for 30's left child. You will see -1, so you'll make null. Now you will make a recursive call for 30's right child. You will see 40. So you will make a node 40 and make its right child. Now you will make recursive calls for 40's left and right children. Both are going to be -1. So left is going to be -1 and right is going to be -1. Now this 40 is constructed, 30 is also constructed. We will make a recursive call for right child of 20. When you make a recursive call for right child of 20, you will see a -1, right? You will come here and you will see a -1, so you will mark it as null. Now this subtree is constructed. You will make a recursive call for the right subtree of 10. When you make a recursive call, you will see -1 in the array, the next element, and you will mark it as null. So your original tree is constructed back. You have deserialized the binary tree. Now you have enough idea of serialization and deserialization process. Please try to write down complete code for serialize and deserialize functions. Let us now see implementation of the serialization part. So I have written serialize function here. In this function, we are taking root of a tree as an argument, and we are also taking dynamic sized array as another argument. And what we are going to do is, we are going to fill this dynamic sized array with the serialized version of the given binary tree. And we are simply following a pre-order traversal of the binary tree. So first thing is, if root is null, if we encounter an empty binary tree, we push -1 into the vector, or we add -1 into the array list. Basically, we are adding an element at the end of dynamic sized array every time. Now, if the tree is not empty, then we are adding roots data and then recursively calling for left and right children, which is simple pre-order traversal. Let's see the working of this solution for this example tree. So this is our input tree. This is how this recursive solution is going to work. It's going to call for 10, then it's going to call for 20, then it's going to call for this null. 10, 20, null. Then it's going to call for this null, then it's going to call for this null, right? Now when you call for 10, you come here, you add 10 to your array. Then you call for 20, you again come here in the recursive call, you add 20. Now when your 20 call is over, you will call for left and right children of 20, which means you will call for null. When you call for this null, you will add a -1. You will come to this part and add a -1. Then you will call for this null and add one more -1. Then this 20's call is over. This call will get the control back and it will call for null, right? This call gets the control back and it calls for null. When it calls for null, you add one more -1. So this is your serialized version of this binary tree. You can notice that number of items in this serialized version is equal to the number of recursive calls that we make. And if we have 2 nodes in the binary tree, then we are going to have 5 entries. So if a binary tree has n nodes, then we have n plus 1 nulls that we can use to represent the whole structure of binary tree. For example, here we have 2 nodes and then we have 3 nulls. If we have 3 nodes, then we'll have 4 nulls. In total, this array is going to need a size n plus 1, which is 2n plus 1. So we have now talked about serialization. Let's now move to the deserialization part. Let us now talk about implementation of deserialize function. So here we are given an array like this and we are supposed to construct the tree. Our output is going to be tree, this tree, and we need to return pointer to this node 10 in C++ and reference to this node 10 in Java. Let's now see how do we construct the tree from this array. So we are again going to follow pre-order traversal. We are going to construct the tree using pre-order traversal. In this implementation, we are passing a vector in C++ and an array list in Java. We have also used an index variable which is shared by all the function calls. Index is global in C++ and a class member in Java. Although it's not a recommended practice to have global variables, we have used it here for ease of implementation. We can pass index as reference to avoid global variables, right? So what we do here in this implementation is, first we check is if we have traversed the whole input array. If we have traversed the whole input array, then index will become array.size. In this case, we simply return null. In other cases, we check if the element at current index is empty, right, -1, then also we return null. In the other cases, we construct a node with the given value. We recursively call for the left part, recursively call for the right part. Whatever left part returns, we link that subtree with the roots left. Whatever right part returns, we link that subtree with the root right. And once left and right are linked with the root, we return the root. Let us now see working of this code with this example input array. Initially our index is 0. We call this function. When index is 0, we do not fall into this case and we do not fall into this case as well, because the value here is 10, not -1. It's not empty, right? So what we do is we come here, we construct a node with value 10. And now we make a recursive call. When we make a recursive call, we again begin execution from here. Please note that before making the recursive call, we had incremented the index. So now we are going to make a call with 20 elements, right? When we call for 20, what is going to happen? We are again going to begin execution from here, and we are not going to fall any of these corner cases. We are going to come here and we are going to construct a node with value 20. Now 20 is again going to come here and make a recursive call. And when 20 makes a recursive call, it also had incremented index, right? So it's going to make a recursive call for this element. And this time we fall into this case. So what we return? We return null. So this call in the 20's parent call returned null, right? This call particularly returned null. So it's going to return null to its parent. And now what 20 is going to do? It's going to make the left of it as null. Now 20 is going to make a recursive call for next index. And next index element is again -1. So this call is also going to return null. So 20's right is going to be null. Now 20 has constructed itself. It's going to return itself. So 20 is going to return pointer to it in C++ and reference to it in Java. So parent call, which was waiting for here for 20 to finish, is going to take the pointer to this 20 or reference to this 20 in Java and going to make its left child as this 20. Now parent call, which was the call for 10, is going to make the next call for right of it. And when it makes a call for right of it, your index moves to here. And index value is -1. So you're again going to return -1. So when you return -1, the return thing becomes right child of 10. Right? Because whatever is returned, we make it the right. So 10's left child is constructed, right child is constructed. We are going to return pointer or reference to 10. So our tree is constructed. We have got the root node, and this is how deserialization works. We have talked about serialization and deserialization processes. Let's quickly analyze the time complexities of these functions. Serialization process takes theta n time because we are going to traverse through every node using pre-order traversal. And how much space it's going to take? It's going to take theta n space. We are going to have 2n plus 1 entries in for a binary tree with n nodes. Now talking about deserialization. Deserialization also traverses through the array using pre-order traversal. So it's also a theta n time complexity process.